Do you hear me now? Or yeah, they should be hearing me now. You see there is a green thing here, so indicating. Okay, before I start, is there any questions about any of the homeworks? Yes. So that is, yeah, a lot of people get confused about that. And the idea is that I can quickly tell you before I start the lecture. So the ensemble average is clear, right? You have a lot of trajectories. You simulate many the same way, many trajectories, and you take the initial point. Of course, mean square displacement has a lot of points, right? Depending on the time has passed as a function of time. If this is your time pass, you take the difference between these two, take the square, difference between these two, take the square, these two, take the square, average. This is the ensemble, right? Instead of doing this, you can also do, assume that you have a very long trajectory, right? You can take the same difference in this part section of the trajectory and in this section of the trajectory or in this section of the trajectory. They are kind of independent because the motion is random. And you can average again, right? You will do with all the time differences. You will do 1 step, 2 step, 3 steps iteratively. Of course, easier way to do this is that if you think about it, it is equivalent to doing like this. You take the same trajectory twice. And then if you are taking the time, let's say difference of this amount, okay? So you shift this one by certain amount and take all the differences between the consecutive. I mean, you take the difference from this to this, from this to this, from this to this, then you get an array of differences in distance for a certain amount of time step through all the trajectory. So you get as a first element, how much I have displaced after the first point when 5 steps has passed. How much I have displaced after the second point after 5 time steps have been. And you kind of get the array, take the square of it and take the mean again. I can tell you in numerical terms what you do is practically. So TMSD as a function of, let's say, time is that I take the time discrete here. You take the first set of elements here, okay? And then you take, and the shift between these two is t, okay? You cannot, of course, take the last t elements here because you need to shift by that much and then you don't have room in the trajectory. And then you take the shifted part of the same, these are the same array. One, you
Excuse
have one
me, I could.
You're taking time average. And you kind of take the difference between the two. And then you get an array of displacements, right? For t. And you take the square of this array and take the mean. And this is only for one t. You change the t, repeat it, change the t. T is equal 0 is the same array. You get displacements of 0, right? T is equal 1 is just when you move them by only one step. Tau and t are some notation just because time is the axis here, right? And then tau is maybe the time difference or vice versa, I think. So I have to use two variables to kind of not confuse between the two. This is what numerically should be done. And also that I realized there is a lot of questions that are emailed to me about the homeworks all the time. So for today is what, Tuesday? Tomorrow afternoon. Yeah, exactly. Tomorrow from 1 to 4. If you need help, you can either come to my office or join the Zoom. Okay. I will try to be mostly online. If you have any questions. Is that clear?
One question.
Or is there a question in the chat?
Yeah, I was just wondering if you could temporarily angle the Zoom camera towards the board, since we see the PowerPoint through screen share anyway.
Okay, let me try because the connection is not I don't know if you can see. I can try to use this board instead. Just a second. Actually, no, I can try to write here instead when I'm writing. So let me see.
Thank you.
No. That is not ideal. I don't like it. Just a second. Okay, I write there and you try to see there when I'm writing. Is this better?
Better, absolutely.
Yeah, okay, thank you. Any more questions about the homeworks before I start? Okay. Then we can start. Today we talk about multiplicative noise. What is multiplicative noise? If there are multiple sources of noise, what is noise, first of all? Is this clear? Like when I was, I come from physics department, and noise from like anybody from communication engineering, it's pretty clear what noise is. But it's not clear to physicists or computer scientists what is really noise that is representing in every system. For example, for the motion of a Brownian particle, noise is the random force term. Anything that is fluctuating can be referred in physics as noise. So this can be kind of confusing. Here, what we refer to noise is the thermal noise in the case of a Brownian particle that is diffusing around. What is thermal noise? These random forces that are acting on the particle. Okay, but noise can be other things. For example, here, multiplicative noise, you will see that, for example, the diffusion coefficient of the particle can vary according to where particle is. That is also kind of another noise. Okay, and here is a kind of we put this picture just because it was fancy. This is a astronomical picture, and these kind of pictures, it's very important because all the sources of noise here, the noise can be the camera gain or can be the deep sky light noise, and also it can be other kind of camera noises. So these kind of add up, and you have to take into account of all of them and how they actually interact with each other as well. Do you understand the difference between multiplicative and additive? Additive means that you can consider all the sources of noise independently to animate or simulate your system or create your result and kind of add them after. Is this clear? Multiplicative noise doesn't work like that. You have to think about how they interact and come up with the solution and correct your problem. Okay, to understand this a little bit better, we have like an exemplification, and here we have a particle that we assume was in the middle in the beginning. Okay, this is a Brownian particle, just the one I was presenting in the Brownian motion lecture. Okay, this starts in the middle, and after a certain time has passed, this particle will have a Gaussian distribution with deviation sigma, and I denote this by sigma 1, which is related to T1, which is after a certain kind of amount of time that has passed. Is this clear? This particle will deviate a little bit from the center depending on how much time has passed. This can be actually theoretically predicted using the Fokker-Planck equation, which is the differential equation by solving the probability distribution over time as a function of time. And if you check the time a little bit later, you see that as a function of time, this Gaussian envelope that represents the probability distribution of the Brownian particle after certain number of steps is going to widen and widen over time. Is this clear? And you will observe that even it doesn't matter if you use a solid boundary condition, periodic boundary condition, or even no boundary condition. You can go to infinity and they will look very similar. The only difference is that if you have a boundary condition that kind of restricts the particle to stay in the box, that will, like, the integral of these probability distributions would have to be the same over the time, because the probability of being in a box, if it is 1, the integral should always be 1. Okay, of course, this is the result we expect, and there is nothing surprising here, right? But what happens if we have a particle that it is diffusion coefficient, which means that it is displacement distribution, the distribution of the steps, or let's say I am operating a random walk, right? I'm going to the right one step, going to the left one step, and repeating this for a lot of time. And if my steps are small so that it doesn't look discrete, after a lot of steps, my distribution will also look like this, right? And assume that for some reason, I cannot take as wide steps as I go to one direction than the other. It can be that, I don't know, that it is cold on this side of the lattice, or I don't know, any other reason, okay? This happens naturally in physics a lot of times, and I will come to that in a while. But now let's say that we have a constant noise. Here, by noise, what do we refer? By word noise, what do I refer to here? The sigma, right? Which is the deviation, or yeah, the deviation of the random steps I take in every time step, okay, for the particle. So if sigma is constant, I have no surprising. I have, after 10 seconds, the particle displaces a little bit, 100 seconds, a little bit further. And these are the, you see the probabilities corresponding. And from the initially being in the very much likely to be in the center, because at t is equal 0, I release the particle from the center, the distribution widens. And after a very long time has passed, the distribution is kind of flat. Particle can be anywhere. Is this clear? Why? Because it doesn't have a preference direction, right? It can go either direction equally likely, and it can kind of end up anywhere equally likely. And it doesn't even matter if you have a solid or periodic boundary condition for this case. It will give you the same kind of probability. Is this clear? Okay. Now we assume that we have a multiplicative noise, which means that the amplitude of the steps I am taking is changing as a function of x. Okay, which means that I am actually taking larger steps if I'm here and taking smaller steps if I'm here. Do you understand what is the difference between this and this? Here I'm taking the same step distribution, independent of my position. Here my step amplitude is changing according to where I am on my x coordinate. Okay, what does this result in practically? Yes, why? Yes, it will take me longer from going from this side to this side, right? You understand the difference? Yes. So it will take me longer from going from this side to this side. If I, by the way, here I calculate the distribution using the standard stochastic integration method. So which here we need to kind of explain what are the different kind of implementations. So when we are taking stochastic integrals, this doesn't have to be only about the displacement of a Brownian particle. It could be anything else. We have a function, and then we operate this by noise, right? And this noise is affecting this function also. So if you take this integral from the, let's say, this according to the point in time where we take the value of the function at the beginning of the step. Okay, this is called Ito integral. Let's say, okay, this is not very accurate, but let's say this is as a function of time, and I take the integral like this according to this point. This is Ito integral. If I take half step and then take this value of the function, this is called Stratonovich. These are written in the and if I take the latest element, this is called anti-Ito integration. And these kind of methods create different results and deal differently against the multiplicative noise. Of course, the physical meaning here is that if we take the standard Ito integration, this is not surprising to me anyway, because if I am slower on this side, it will take me longer time to reach the other side. Is this correct? Is this intuitive? If I'm taking smaller steps, I somewhat come here and it will take me longer to go to the other side. And as a result, I will be spending more time on this. However, in physical systems, when you include both temperature and the diffusion coefficients kind of independently, temperature is the source of kind of the displacement of the particle, right? However, the diffusion, the steps, the step distribution is affected not only by temperature, also by viscosity. So if it really makes a difference in a physical system, if the thing that is deviating is the viscosity or temperature. Why? Because assume that we want to measure forces in these kind of environments. How do I measure forces stochastically? How do I measure forces for a deterministic system? Let's say I want to get the force as a function of distance. I want to map it. What do I have? I have a trajectory of a particle, right? I have the parameters here at this position, x, and I have the particle's velocity on this. These are my measurables. And I kind of calculate what happened to in the next step. And I can directly calculate the force acting on the particle on this position, because everything is deterministic. In stochastic experiments, we cannot do that. What we have to do is that we have to kind of, so, oh, that was not smart. Because each time my particle has reached a certain point in space, is going to be ending up in a different location in the next step, right? Because there is random terms. But what I can do is I can check every time the particle has been, for example, in a certain area in space, a very small area, and check this, what happened to the particle displacement in the next step. And I can try to take the average of this, and this will get me the force, right? This is called drift method, essentially, in experiments. So I kind of get what is the average displacement, this, and I say that, okay, the force acting on particle is in this direction and this amplitude, depending on the average displacement of the particle. Is this clear? However, if my diffusion steps, amplitude of the steps are changing like this, this will give me a fake kind of force value that doesn't actually exist. Is this clear? So this can be, and in nature, if there are no forces and the temperature is the same along the space, the distribution will actually, the physical distribution is still going to be like this, even if my step distribution will change due to the change in viscosity or fluid dynamics, which I will come to in a second. Okay. But in what condition in nature the diffusion coefficient changes over the space without temperature changing? What could cause that? Or I can rephrase the question like this. What causes the diffusion of the particle inside the liquid environment? What is the source of the vibration of the particle, fluctuation of the particle inside this liquid? Collisions with other molecules, right? And what could create an asymmetry in the diffusion coefficient across the space? If the space is not homogeneous, right? An example of a space that is not homogeneous is this. Think about a spherical Brownian particle inside the liquid environment, right? and it's approaching to a physical wall. What happens? Yes, there is a question. I know. Okay. What happens? The particle approaches the wall. Or another question: what happens to the fluid molecules approaching to the wall? Which ones are faster? The water molecules that are inside the bulk or near the surface? Has anyone taken fluid dynamics kind of course here? Something similar. There is something called the no-slip condition in fluid dynamics, which means that the fluid velocity cannot be positive near the surface along the surface direction, because here, if there is a bulk of fluid that is flowing in this direction, it will have a high friction with the surface that is solid and all the molecules are stationary. This, by the way, doesn't mean that these particles don't have any velocity. They still have a lot of velocity in the degree of freedom of vibration. But in terms of their translational degree of freedom, which means that a molecule can have velocities in different kind of freedom, degrees of freedom, right? It can translate in one direction. An air molecule is, for example, an air molecule and a solid molecule on this wood inside a molecule, they have kind of similar average speeds. What is difference? Because they have the same temperature, right? But what is the difference? The kind of form of the velocity different from the air molecule to the solid one. This one is mostly vibrating. This is still because it is potential energy profile is confining it in a place that it cannot move, whereas the air particle is a lot freer. It can go because it is not. It doesn't have a kind of this kind of packed lattice structure or anything like that. So it kind of going back and forth all the time. So it is velocity is kind of translational. And here, as you come close to surface, liquid molecules, even if they are liquid, they can actually translate. Their translational degree of freedom is really confined. As a result, particle motion is limited because it is also this particle, this big particle's motion is resulting from the collisions from the water molecules, right? This is a hydrodynamic problem. Of course, it's very complicated and even numerically difficult to solve, but also analytically, this is possible to solve. And people have shown that these are the functions that how the particle's diffusion coefficient is affected by coming close to a surface. A particle of radius r, you see that if it is getting significantly closer to the surface than its radius, this is a logarithmic scale, right? If it is getting a lot larger than if it is far away from the surface, there is no problem. The diffusion coefficient that is parallel to the surface or perpendicular to the surface are equal to each other. But especially if it is getting very close to the surface, approaching very close, its diffusion coefficient perpendicular to the surface is dramatically decreasing a lot. Yeah, it's approaching zero. And the other one, the parallel, is also decreasing because even in this direction, particle is moving less because liquid molecules are constricted there. Is this kind of intuitive at least? Yeah, because this is not what we are going to worry about so much for the rest. What we have as a result is that we have a derivative of the diffusion coefficient as a function of distance. And these are the results for different kind of particle radii. You see that as the particle radius gets smaller, it is affected. I mean, it is the same if you rescale the system, of course, but if you are considering the similar distances to a surface, smaller particles get affected less by this than the larger particles, okay? And as a result, this creates also problems in experiments. So this is an experimental setup, and this is the experimental paper I will talk about now. And this is very well connected to multiplicative noise and the simulations we are making. I am trying to create here an intuitional background. Why do we care about this? Because it has an immediate consequence in the experiments, okay? So here, what we have is we have a total internal reflection microscopy. This you don't need to know anything about. I will just explain with 2 sentences. There is a laser beam that is coming to this surface, and the angle is in a way that this is high refractive index, and this is the liquid environment, this is glass. So it is kind of reflecting. It's happening. This is, you know, in optics, there is this limit, a certain threshold of angle. If it's coming to a lower index of reflexivity with a higher angle than a certain angle, it's kind of having a total internal reflection. But what we don't learn in linear optics is that actually there is an exponentially decaying stationary waves on the other side that don't actually propagate, but they are there. And the particle, if there is a particle here, it can interact with those lights and it can scatter these waves. And these can be detected. And with this method, you can actually measure very accurately using a laser beam the distance of a particle, of a small particle from a surface. So with experimentally, you just have to, this is the, like you have a detector here, you kind of try to measure the scattered light from here at the detector. And this is the profile of the intensity you measure as a function of particle Z position. Okay. And you have a data at the end, you can kind of obtain in the detector from the scatter light. And from that data, you can kind of create the position trajectory of this particle. Why this is important? Why this is better than standard microscopy? Because in standard microscopy, I deal with images, right? Images can be at 100, 200, 300 frames per second, whereas this signal is purely electronic and it's connected to a sensor that is, yeah, collecting the light intensity. I can measure this trajectory at much higher frequencies, hundreds of kilohertz, for example. And another advantage is that it's very difficult to calculate, even if there is a depth of field. If you have a particle getting in and out of focus, it's very tricky to calculate the Z position of a particle from a microscopy 2D image, right? X and Y, you can kind of track. Accuracy is not, even if it's not as high as such system. But here we are interested mostly in the Z component because we are kind of making an experiment of a particle near a wall, okay? And what do we observe? We are looking at the displacements of the particle, okay? In short time scales and also in long times, a little bit longer delta T. And what I'm changing here is the time step. And you see here is the particle position distribution, position displacement is totally symmetric if I am looking at the particle in a very short time. But as soon as I'm looking at the particle in a little bit longer time scales here, you see that it is kind of distorted significantly from what we expect, right? Why is this happening? This is happening due to the fact that the particle is changing diffusion coefficient. It is moving a lot more if it is here, right? And if it's moving a lot less if it's closer to the surface. There is an asymmetry. Why doesn't it show its behavior as strong on the bottom part? No. It is a difference in the initial position of the, so this particle is further away from the surface, okay? The one in the bottom is further away from the surface if you compare it to this one, so that it is affected, the effect is less. Is this clear? So let's see, let's assume that I want to calculate the force acting on this particle. Okay, as a function of distance, as a function of the distance of the particle from the surface. This is for this particle very straightforward because we can calculate it, because there is only the gravity that is pointing downwards, and there is the interaction between the glass surface and my particle. That is the repulsive interaction. And I can calculate this theoretically, and I can almost be sure what is the expected force values that I can measure. And here are the results that the experimental force values. And here they are measured with 3 different methods. One is, the first one is that I can get the distribution of this particle, right? I have the position distribution and I can assume what is the potential has to be. I kind of apply the Boltzmann distribution, which is P of Z should be proportional to e to minus P of Z divided by kBT, right? This is the Boltzmann rule. And we actually assume that the temperature is constant. This is very important. This only holds if the system is in equilibrium, which means that the temperature across the space is constant, which it is for this experiment. And I can kind of, from this distribution, I can get the potential energy, and I can take the derivative of that. And that is called the equilibrium distribution method. So I have the distribution. From that, I can calculate the potential, because I know that it's expected to obey the Boltzmann distribution. And then if I know the energy as a function of height, I can calculate the force. Do you have a question? No. Okay. This is one method. And the other method is that I can actually calculate the force according to the displacements of the particle. I check each time, as I just showed you, where the particle was and where it went in the next step. And I can do it in two different ways, okay? First method is that I can look at the particle many times when the particle was in this box, and I check where the particle has gone in the next time step, and I calculate the force according to that, right? And that gives me these solid circle disks. You see the measured force values. It's not consistent with equilibrium distribution method. It's not consistent with the theoretical expectation either. This is due to this spurious drift that is happening here. That makes me think that this is a force acting on the particle here, but it's not the force. This displacement asymmetry comes from the fact that its diffusion coefficient changes along the space. Is this kind of clear? And how can we deal with this? Instead of taking this approach, okay, I do the following one. I kind of take the same thing a lot of times when the particle was in this box. And instead of checking where the particle went to, I check from where this particle came from, to this point. Where was this particle in a certain amount of time ago? And for those ones, and I kind of calculate the displacement, where this particle come from to this point. I kind of change my approach, and I calculate the force acting on the particle in this way. And in that case, I kind of get this drift method for alpha is equal 1. And this gives me the correct force values acting on the particle. Okay. This is due to the fact that the stochastic integration using the Ito method, what is called this alpha is equal 0, is we take the values from the beginning of the function, any function that is acting on the particle. This doesn't apply only to, there is a very nice review paper on that Jan Weir and Giovanni wrote together. It is about reviewing these kind of things. These effects don't only happen only in this kind of system. This is just a system and an experiment that is representing it in a beautiful way. So it is intuitional. We understand what's going on. We know the physics. We know why these kind of asymmetries should not reflect in the probability distribution, because it is the same temperature. It should be, if it's in equilibrium, the distribution should scale with the potential energy. It's the same for this problem. If I have a Brownian particle that I leave the particle here with the temperature is constant, it should have a flat distribution. But what is the difference between if I am simulating an overdamped particle with only changing the diffusion coefficient as a function of space? I won't really observe. I will observe kind of this one, right? What is changing in reality when I have from a simulating system to a real system? In a real simulation or in real life, we have a, let's say, what is my equation, like overdamped Langevin equation? We have x prime that is equal to minus gamma x dot. This is the derivative of with respect to time, and then square root of 2d times w, right? here I can check that I can tell that my W is a function of distance, or my diffusion coefficient is a function of X. Okay. Of course, here my diffusion coefficient, if it's a function of X, there is also a temperature. My diffusion is often dependent on temperature. So here is what is my diffusion coefficient here for a standard Brownian particle? This is 2 kBt gamma, right? If this is changing due to the change in temperature, this is very different, because then we are not changing this term. You understand what I mean? Yeah, we are not changing this term. And if it is changing due to the change in temperature, it is only a change in this term, not in the friction term. Is this clear? By the way, this is not X. Yeah. So, but if it is changing due to the change in friction or liquid properties, viscosity, it is the gamma term here that affects the particle diffusion coefficient in a way. And this is due to the configuration of the space. This is often gamma that is changing effective friction or the viscosity acting on the particle due to the fact that it is close to a surface or any other boundary, another bigger particle, blah, blah, blah. This may happen also if you have two particles that are close to each other. For example, think about two spherical particles that are getting very close to each other. They kind of limit significantly the motion of the liquid molecules between them. So that their diffusion coefficient, which means their gamma, this is a hydrodynamic relation between these two particles, is going to change as they change the distance, interparticle distance between each other, right? However, if the temperature is constant, then we know that all the distribution laws from the physics has to be satisfied. Of course, if the temperature is not constant, then we can kind of observe this kind of physical distribution behavior. Also, it can be physically valid as well, which means that it is only the step distribution that is changing, not the friction, not the viscosity. This creates asymmetry in real life distributions as well. We get something like this. And this is called thermophoresis. You can look up. If we have a liquid environment or air environment, and we have a thermal gradient, the temperature is higher on this side of the room than this side of the room, you will observe that over time, particles will displace from the higher hotspot. They will go to the cold areas. This is because when the environment is hot, their effective diffusion coefficient is increasing a lot, but the viscosity is constant. This results in an asymmetry in real life. However, for the case of Brownian particles, if the diffusion coefficient is changing due to the changing gamma, it is the same gamma here. So this kind of, it is because we can actually divide this equation by gamma and put this here, right? But this doesn't, this division operation in reality, as we do it just by in the stochastic differential equation notation, that brings an extra term that is solved in this kind of review paper. It's not a very, very complicated. It's just a few lines of theoretical derivation that brings another term that takes my system from this to this kind of. I have to correct for that additional term if it is the gamma that is changing. Okay, this chapter is only about that, and you can see that this is the this is the actually the approach I should take, because if I take this alpha is equal 1, which takes into account this correction term, and I mean, you can either add this correction term in your mathematical formula, or you can kind of take alpha is equal 1, which means that you kind of, instead of taking the next step where the particle has been in this position, look at the times particle has been here and check the next step. Look at the time where particle has been here, check from where the particle came to that point. So we kind of change our approach to the problem and we can correct it. And we see that the experimental, and this is the same reference, sorry that I'm missing here, but it is the same reference to the same paper here. Okay, so this can be corrected in terms of force measurements. Is this clear? So it's important, if the diffusion coefficient is changing due to the change in temperature or due to the change in friction coefficient or the viscosity term. Okay, if it is due to the liquid environment or a constraint, for example, it could be that the particle is near a wall or two particles are close to each other. It is due to the configuration of the space, that is limitations of the liquid molecules, and it is the friction term, the drag term, that is changing in the equation, and it is changing in both of these terms. And that at the end, if you think about the distribution of a Brownian particle, gamma doesn't play a role there. It is only a potential energy divided by kBt. Even if gamma is changing over the space, it should not have an effect on the distribution of the particle. However, if the temperature is changing as a function of the coordinate, if the thing that is changing is temperature, that will create a drift in the particle motion. And this is also experimentally valid and relevant. People have measured this. People use this for experimental setups and manipulating particles even in the microscopic environment. And this effect is called thermophoresis. So these two things are a little bit different. The things we discuss in the book lecture chapter is where the diffusion coefficient is changing due to the different configuration of the space when the particle is changing position. We assume that the temperature is constant. Okay, is this clear? Any questions about this? Okay, then we can pause here, and in the next lecture we will talk about Vichek model. That is about how particles align with each other and kind of operate this kind of collective behavior or motion. Let's see.